Welcome everyone, we are the UPC21 team and we are representing the ACI student chapter from the Peruvian University of Applied Sciences from Lima, Peru. At the world level, solid waste management becomes a serious problem. In this sense, the final disposal of end-of-life tires has become to represent a technical, economic, environmental, and public health problem for many countries. Peru is not exempt from this problem. With a fleet of almost 4.5 million vehicles, this leads to a series of excess tire waste, of which many of these tires end up in the Ate district, known for being one of the largest tire stockpiles in Lima, or simply lying in some corner of the capital. It is known that in various areas it is customary to accumulate tires on the roofs or domes near the houses. Then, with the rains, artificial pools are formed inside, generating ideal places for the proliferation of the mosquito, which is the main vector of dengue in Peru. Also, Peru doesn't have a specific regulatory framework to deal with the problem of treating end-of-life tires. In addition to this, the current Peruvian reality, in which it stands out that the less favored population located in Lima tends to build informally and without professional assistance, existing high seismic danger. These houses have stability problems, affect the quality of life, and have high seismic vulnerability. In the peripheral areas of Lima, 90% of the houses are self-built. Also, it is estimated that self-construction houses would suffer 29% damage in the event of a seismic event in Lima. So, what could be the solution?
The rubberized concrete is a new construction material. It is created by incorporating rubber particles that came from recycled tires to common concrete mixes. This addition impacts in a positive way on the mechanical properties concrete and also in the environment due to this concrete use recycled materials. According to James Shrey and Masanobu Shinosuka, rubberized concrete could be used as an earthquake-resistant structural concrete due to energy dissipation properties that it possesses. The rubberized concrete compounds are similar to those used in conventional concrete, except rubber particles additions. This replaced by volume a percentage of coarse aggregate. The replacement percentages range between 5% and 20%. The final properties of concrete depends directly on the percentage of substitution that the rubber has on the coarse aggregate. For structural concrete, the percentage of rubber particles must be 50%, which achieve the optimal properties of the concrete. Following the provisions of ACI 211 and considering a water-cement ratio of 0.45, the mix design would be as follows: 297 kilograms of cement, 152 liters of water, 882 kilograms of fine aggregate, 887 kilograms of coarse aggregate, and 52 kilograms of rubber particles. All these values correspond to a volume of 1 cubic meter of concrete.
The tire recycling process consists of separation. Using specialized recycling machines, the rubber is effectively separated from other materials and dirt that used tires may have. Shredding. It can be done in different ways, mechanically or chemically. The mechanical tire shredding process is the most common and economical. It allows to reduce the volume of the tires to the maximum without using chemicals or adding heat. The used tire is passed through a continuous line where it is cut, crushed, and compacted until the tires are reduced to a size so small that it looks like black rubber sand, in different ways depending on the use that is going to be given later. In the case of concrete, it is reduced to a size of 6 millimeters, replacing the coarse aggregate.
The use of rubber in concrete can be a good option to recycle it and regulate its uncontrolled use. For example, in countries like Spain, there are approximately 100,000 tons of rubber wasted without use. These are part of the 10% of microplastics from the world sea that damage the ecosystem and marine life. These tires must have a use. Additionally, rubber gives concrete some interesting anti-seismic properties. Rubberized concrete reduces the average damping in the columns by 62% and reduces the seismic force. However, it has low compressive strength, up to 40-70% less than conventional concrete. That is because the rubber absorbs plastic energy and the union between rubber and cement is bad. Fortunately, exist additions like silica smoke that improve this feature. Rubber also provides the concrete properties such as acoustic insulation, greater durability, and greater hardness.
Comparison between conventional concrete and rubberized concrete. The cost of cubic meter of conventional concrete is $62.58. Its endurance is from 170 to over 400 kilograms per square centimeter. However, rubberized concrete is 2.9% cheaper than conventional concrete. Its endurance is from 170 to 250 kilograms per square centimeter. Also, rubberized concrete reduces the carbon footprint by 0.4%. Conclusions. First, rubberized concrete is lighter than conventional concrete. Second, a concrete structural element with rubber has a damping factor superior to conventional concrete by 62%. Third, on average, adding rubber crown into concrete reduces seismic response acceleration by approximately 27%. Finally, rubberized concrete is 2.9% cheaper than conventional concrete. Furthermore, it reduces the carbon footprint by 0.4%. And Chatapuni Chaiki.